Hello, welcome ladies and gentlemen. Nice to see you all here, lovely to see you all here at this meeting at the Institute of Physics, which will be the last time we will have a London meeting until September. October. Oh, that's right, until October. We have actually technically two meetings here because of what it says in the bylaws. We have to have an annual special general meeting, which is a very short event just before the talks today. And this is specifically to consider subscriptions for the next year. The founders of the association felt it was very important to have a meeting every year for the members to actually vote on the levels of subscriptions, and that is a tradition which still maintains. And so I will introduce our treasurer, Dr. Geoffrey King, to present to you his reasoning and his proposal.
Thanks, David. Okay, this should not take long, I hope. Where are we? Slideshow, start, where's the start? Play slideshow, media controls, use presentation view, where's the start? What can I do?
From the beginning.
Oh, there we go.
It's not a touch screen, guys. You have to...
What?
Yeah, no, there you go.
Okay. So, before I describe to you the fact that we're not going to do anything, I'm going to tell you why we're not going to do anything. And we are a charity, all right? We have resources of £1.5 million. So we are much better off than a lot of our members are going to be by the end of this year. And even allowing for the turmoil that's going on right now, we continue to be in very good financial health. Okay? We do spend more than we get in subs. We do rely on the investments that we've got. But even if the investments go down a bit because of what's happening in Ukraine, we'll still be in very good shape. But many of our members will be feeling the pinch because of 10% or whatever inflation's going to be. So in view of all that, the trustees decided that the subscription rates should remain the same as the previous year, which is the same as the year before. So this will be 3 years in a row where we'll have the same subscription rates, okay? And those rates are these, which you can find on the website or wherever, but there's no change at all. Now, we had a discussion amongst ourselves as to whether we should actually reduce the rates. But as I said, we spend more than we actually get in subs and so on. So we made the decision not to reduce them, to keep them as they are. But there is a mechanism by which if people are really hurting, we do have resources to make it up for them. So, would anyone like to propose that we do this? Because apparently we have to vote on it. Okay. Nick and David, I guess you'll second it. Right, okay. Can I ask for a vote on, well, does anyone want to say anything about it to start with? Anyone object or? Okay, so if no one objects, we have a proposer and a seconder. Anyone in favour? Okay, I think that's pretty unanimous. Thank you.
Anyone against?
Is anyone against? Yes. No.
Would anybody like to abstain?
Oh.
An abstention.
Oh, hello. I'd have talked to you earlier if I'd known. Okay. Right, thank you. So that's it. Right, okay. So we don't need. Where's Mike? There's Mike. Down there. Get rid of that.
I'd like to invite any new members who are at a BAA meeting for the first time to be welcomed into the association. Is anybody a new member attending or recently? Or yes, one gentleman over here. Would you like to come up, sir?
I didn't know this was going to happen.
You're allowed to decline. You're allowed to what's your name?
Duncan Hale Sutton.
Duncan Hale from
Hale Sutton. Yeah.
Hale Sutton.
Yeah, double barrel, sorry.
Well, it gives me great pleasure to welcome you to the BAA, and I hope that you enjoy your membership and that you stay with us for many years.
Thank you.
I now like to ask the Papers Secretary, Jeremy Shears, to tell us what papers have been approved by the Council.
Happy to do so, but just to add my personal welcome to Duncan, who's submitted his first observations of variable stars to the database this week. So that's an excellent, first of many thousands, I'm sure. So 2 papers were accepted for publication in the Journal at Council this afternoon. So there's Uranus during the 2016 apparition by Kevin Bailey. And the second one is Backyard Lunar Mineral Prospecting, Measuring Titanium in Mare Tranquillitatis. It's a joint co-authorship between Mark Kidger and Juan Jose Carrera. They'll be in the Future Journal.
Thank you, Jeremy. I'll mention briefly our forthcoming meetings and try and encourage you to come to some of them. We have, on the 25th of June, we have our one-day summer meeting. We hold the summer meeting every year in a different city around the UK. And this year, on the 25th of June, it's in Nottingham. And we are the guests of Nottingham Astronomical Society. And this will be a whole-day meeting on a Saturday. And the topic is cosmology, galaxies, and exoplanets. So all the talks will be about those very popular subjects and cutting-edge subjects. So I'd like to encourage you to book for that via the BAA website through Eventbrite. There's plenty of space. There is, and the next meeting after that will be in September, and that will be the weekend meeting in Scotland, Elgin in Moray, and we are guests of Moray's Astronomy Society, and that will be Friday the 9th of September at 7 p.m. until Sunday morning, the 11th of September. We have Radio Astronomy Zoom on the 3rd of June on high-resolution radio observations on supermassive black holes. So that is, and you can get the details of that from the website, how to join in with that. And then the next BAA meeting here will be 26th of October, and that will be the annual general meeting, at which the and that's the start of our year then. And you will, in the meantime, you will have had the ballot at the same time as you have the journal, and the ballot is for you to vote on the council and president and everybody. But I can tell you now that the number of candidates has not exceeded the number of posts, so it may seem a bit pointless voting. But I'd like to encourage you to return the ballot and do it online. It is very quick. It just shows a certain level of interest and participation by the membership. So those are the notices. I will now move on to our first talk. Mike Fuchs. Mike is going to give the George Alcock Memorial Lecture. So every year at this time of year, we have a lecture in memory of the great observer, one of the greatest ever amateur observers and members of the BAA, George Alcock, who discovered 3 comets, I think it was, and 3 novae. Oh, more. Sorry, I've got it wrong. 5 novae?
Yeah.
5 novae. How many comets?
I should know that, shouldn't I? 5 and 5.
It may have been 5 as well, yeah. I think it was equal numbers of comets and novae. The George Alcock Memorial Lecture doesn't have to have anything particularly to do with George Alcock, but it's on an aspect of observational astronomy. And actually, George Alcock, earlier in his career, did do quite a lot of planetary observation. And Mike is our Saturn, Uranus, and Neptune section director. Mike has been interested in astronomy since he was 7. He particularly enjoys observing the moon and the planets and visiting total eclipses of the sun. He works in the spacecraft industry. And so here is Mike to talk about great storms on Saturn.
Fantastic. Right, hello everyone. I don't know if we say good afternoon or good evening at this time, but first of all, I'd say I think it's a great honour indeed to be asked to do the George Alcock Memorial Lecture. As David has said, he is an absolute legend. Everybody knows about him. I did some research and it is 5 comets and 5 novae. He was a very dedicated observer as well. And my first encounter with George Alcock, I heard a couple of talks by him way back in September 1981, when some of us had a bit more hair than we have on our heads now. And bands like Adam and the Ants, who I didn't particularly like, were top of the charts. And he gave this talk at the Horncastle Astronomy Weekend. It's something similar to Winchester. And needless to say, competition for the front row seats was fierce. But he came over as a very knowledgeable man, a very dedicated observer, very modest, but he had a wicked, dry sense of humour. As we've already heard, he discovered 5 comets and 5 novae, but he did a lot of observing in other fields as well, and indeed looked at the planets using nothing more than a 4-inch or 100mm telescope. And maybe the view that he would have had of Saturn might have been this. He might have seen the main rings, the Cassini division, and perhaps 1 or 2 bands. And this is the sort of appearance you get with a small telescope. And often as not, even with larger telescopes, this might be as much as you may see. But over the years, we've found that there are actually atmospheric features that occur on Saturn, not as lavish as those on Jupiter, but some of these require large telescopes. Some features can be seen with relatively modest things. But undoubtedly, the greatest, most dramatic, most interesting features are called great white spots or great storms. And we'll see they do exactly what they say on the tin. They initially start out as a very bright spot on Saturn. We call things spots, even though it blaze their size. And these can often be seen with quite small telescopes. They then sort of expand a little bit. They rapidly expand in size, so they become bigger, so easier to see. They are often as not expand around the planet. They expand both in latitude, over land base of latitudes, but eventually the disturbance encircles the planet at all longitudes. And after a number of months or so, it sort of dies down again. To date, there's been 6 of these great events, starting in 1876, and the last one occurred in 2010. I'm going to look at this one in a little bit more detail. Initially, obviously, many of the observations of the early storms were made visually with drawings, but eventually photography got on there, and by about 1990 was interesting because not only were amateurs switching to digital imaging as well as visual observing, the Hubble Space Telescope was in orbit, and this gave unparalleled views of one of these storms. Things have moved on into 2010. Hubble still up there. Many amateurs were expanding their digital imaging techniques, visual observing, go on. But 2010 was a landmark one for observing one of these stories, because we had a spacecraft in orbit around Saturn, which gave unprecedented views of the planet. And this was the Cassini orbiter. It carried the Huygens lander, which went on to Titan. Huygens named after Christian Huygens, who discovered Titan. And of course, Cassini, named after Jean-Dominique Cassini, who discovered the Cassini division. And this was an absolutely fantastic spacecraft. Interestingly enough, it got into orbit in 2004 around Saturn. Its original mission was only for 4 years. So if they'd curtailed that, it would have been 2008, and they would have missed this great storm. But fortunately, money was found, and the mission was extended. And on board the Cassini orbiter, there was 12 instruments. Each of these have got the usual NASA acronyms for them. I've listed here the sort of basic things these experiments were going to look at. And all of these probably contributed in some way to looking at the storm at Saturn. But there were 3 in particular that were very important. Obviously, the imaging subsystem, and these were 2 telescopes, wide angle and narrow field. Something called the, I've lost my place now. There's the imaging system. There was something called VIMS, which looked at the spectra of things. And this actually discovered ice crystals in the storm. And interestingly enough, there was a plasma wave radio experiment on board as well. This detected radio waves around Saturn. And not long after the spacecraft had gone into orbit in 2004, it detected radio waves which the scientists said were actually radio waves emitted by lightning bolts. And these were strongly correlated to some small storms that were seen in the planet's southern hemisphere. And indeed, some of these storms were quite easily seen by amateurs using 200mm aperture telescopes or above. This plasma waves experiment on the 5th of December 2010 detected the first indications of what would become this major storm. It detected the radio emissions. This storm may have occurred a few days earlier, but I don't think the experiment was operational, if I remember correctly. It was then fortuitously imaged by the Cassini spacecraft as a small, bright cloud just there in the northern hemisphere. And straight away, I can see everybody asking, well, these images are inverted rather than having north upwards. I have no problem with putting amateur images with north upwards rather than the traditional way of south upwards. But for various reasons, as we'll see later on, I've produced a load of strip maps, not all shown here, which are normally shown with time going down the y-axis and longitude increasing from 0 to 360 from left to right. And this goes for some of the drift charts as well. And it was easier to just invert some of these images with south upwards, and you can see the relationship between these drift charts and the images that are shown south upwards. Who was the first amateur to observe this thing? It depends which society you go to. But certainly, there seems to have been a Mr. Akimura, if I pronounce his name correctly, in Japan, who may have certainly imaged this spot on December the 5th, the same time as Cassini. Now, I actually have seen this image, but haven't got really permission to use this. And other societies may have other images around this time. But certainly one of the first ones that's into the section was done by an Iranian astronomer, Sadegh Gomez. I'm not sure how to pronounce the name. And you can see this small white spot. It looks innocuous. But a few days later, this image by Anthony Wesley in Australia shows how this has expanded. It's living up to the names, how one of these great white spots come about. Early observations were also made with some filters. And here's some by Tommy Kutsu in the Philippines. We see a colour image. We can see an infrared image. And this one was taken in methane waveband, around 890 nanometers. There's a lot of methane in the atmospheres of the giant planets, and this is highly absorbent of certain wavelengths in the red infrared region. And therefore, to cut a long story short, if something's bright in methane, it means it's relatively high up in the troposphere of the planet's atmosphere. Interestingly enough, it doesn't look as bright as the other images, and in fact, only a few methane images were made over this period, and none of them really show the storm that well. And this is probably the best one showing the initial eruption of the storm. Now, Saturn, like Jupiter and other gas giants, have winds in its upper atmosphere that vary with latitude. This is an image of the winds profiles taken by Cassini and Voyager. It's got north up, and it's been annotated by our very own Dr. Richard McKim, who's overlaid a lot of the BAA results, which have been translated into wind speeds on this, and they show a very good correlation. It's also, these squares show where some of these great white spots have been observed. Some are in the equatorial regions near the equatorial jet. One has been seen in high northern latitudes near a westward moving jet, and the one in 2010 occurred with a mid-temperate latitude near one of these jets. So it's actually moving slower than our standard longitude system that we use on Saturn. To show the evolution of this storm, I've prepared a large number of strip maps where we have longitude going from 0 to 360 in what we call the System 3 longitude system, and this is date going downwards from where it was first discovered to the end of December. On the left-hand side, you'll see all the observers who have made this, and all these strip maps will eventually go on the section webpage. And what I've tried to do is when several observers have observed on the same night, try and get the most highest resolution image, unless there's something unusual. Other observers are shown in brackets. Straight away, this illustrates a few things how this storm evolved. The head of the storm actually was moving very fast with respect to our standard longitude, just under 3 degrees per day. Secondly, although the storm occurred at this latitude, at its southern edge, a large number of bright clouds and waves started to appear. And we can see 3 of them here and 3 more here and 3 more there. They're all the same things. In fact, their southern edges started to move a bit faster than the rest because there were stronger winds there. As well as in increasing in brightness, the head was pulling away from the rest of the storm, and a number of other bright features appeared to its north. So straight away, the actual activity that was occurring wasn't occurring at one latitude. It was occurring at several latitudes. For many visual observers might have taken this also as a sort of large spot, but high resolution shows this is the head of the storm. As these things were moving away in that direction, and this was moving a couple of degrees in that direction, eventually, as we'll see, the sort of head caught up with the tail of this storm. Jumping ahead, many of the professional scientists working in this believe that this storm was quite deep-seated in the atmosphere and was interacting with the winds around it, causing all this sort of turbulence, vortices, clouds, wave, call them what you will. And of the vortices that were produced, the most interesting one occurred sort of roughly around Christmas. It just appears as a sort of dark spot there. It's not particularly prominent. And this eventually got the name of either the dark vortex or the anticyclonic vortex. And in many ways, this was almost as an important feature of the head of the storm. It seemed to have been spawned by the main storm itself. As I said, the head of the storm was moving westwards at a fair rate, and in its wake, there's all sorts of turbulence caused, and it looked like a comet in reverse. And eventually, after about 50 or 60 days, the head caught up with the tail disturbances caused originally by this storm. You can see this in this nice picture by Stefan Buda from Australia, and also very faintly there's some storm activity here. So you can see actually, although the storm is at that latitude, it's causing disturbances even further south and north. And this comet appearance was something you see in a lot of the drawings and images that were made at the time. The storm head itself, this bright white feature, did seem to vary in brightness a little bit, and sometimes that sort of comet's tail will get very fainter. But one of the underlying principles, I suppose, of the BAA and other amateur organisations, things like the Association of Lunar and Planetary Observers in the States and Japan and elsewhere, one of the big things that we do is encourage cooperation in observations, pooling observations together, because one observer can't cover everything. So if we have loads of observations, we get a better picture of what is going on. And certainly during this period of when the storm was up, we had a large number of observations coming in, sometimes several on a night. Certainly during March and April, the temporal coverage was great. There was observations every day. And because some observers were distributed around the world, we sometimes got observations where showing the same side of the planet, roughly one rotation of the planet apart. And here's a good example. Here we have an observation on the 9th at 1440, observation a little bit in 10, just after midnight. And this shows the same area of the planet. And although the telescopes used were a little bit different, the seeing may have been a bit different, the resolution may have been a bit different, I think you can see just after the storm, this has sort of brightened up quite considerably. And so even on one rotation of planet with good resolution images, we were seeing changes. Sometimes, however, we just saw that we could see the motion of the storm relative to other people. This image taken by Australian amateur Trevor Barry shows the storm almost lined up with this feature and these two features there. One rotation later by British amateur Dave Tyler, you can see the storm has actually moved relative to these two features as well. And again, you can see that the activity has spread to a number of latitudes. Although the storm head was fairly stable, a lot of these spots seem to come and go. And tracking these was rather difficult because some of the resolution of the images and drawings that we've got varied from time to time. But some of these seem to be fairly regularly spaced by about 10 or 15 degrees or so. Many observers made visual observations, and I think certainly the storm could be imaged with quite small telescopes, images taken with something like a 5-inch, 120mm telescope. In fact, David Gray, who is a very accomplished visual observer, actually observed the beginning of the storm when it's this big white spot with nothing more than a 70mm or 3-inch refractor. For many observers could see some of the things. We see observation by Paul, which shows the head of the storm there. Probably doesn't show up too well on this image, but actually the head of the storm is shown in this original drawing by Italian observer Gianluigi Adamoli. Richard McKim and David Gray were lucky to be using 400mm plus aperture telescopes, and they almost picked up the comet tail from the storm here. But sadly, I think if you were using a telescope of less than 200mm aperture, say 150mm or less, many people couldn't see a lot of this fine detail. The region there might be bright, so it was lucky that a lot of observers were using slightly larger telescopes to see some of these things. I mentioned this dark anticyclonic vortex that came out when the storm erupted. And needless to say, this is a Cassini image. It's orientated with north up. There's 3 frames shown in animation. And you can see that it's spinning clockwise, like it's anticyclonic in the northern hemisphere. And this became one of the major features of the storm. It's often associated with bright clouds on its northern edge. And in fact, you'll see some of these bright clouds shown in the amateur images. And it was big, it was huge. It was about 12,000 kilometres across, which is comparable to the size of the Earth. So, you know, that is a big vortex, it is huge. Certainly the biggest one that's been recorded on Saturn. In amateur observations, it was picked up on some visual observations, also in images. It initially appeared surrounded by all this white cloud and as roughly a dark spot. But it started to show changes as time went on. Here we see an image by American observer Wayne Yeshka, and it appears a little bit darker, and there's one of them white clouds we saw earlier located around it. Over the next month, however, there's an image by British observer Martin Mobley, it started apparently to get bigger. In fact, by the time we got into March, end of March, you can see it's even more elongated. And this image, taken by Filipino imager Chris Go, who's fairly well renowned, shows this huge elliptical object. If memory serves correct, I think a lot of people on email talking about this storm liken this as the Saturn's equivalent of the Great Red Spot on Jupiter. But as you can see, this probably at the front, it's not regular, there's sort of bright clouds on it. And it begs the question, was the vortex itself expanding, or was the vortex inside this darker material that's formed around it? And that's a difficult question to answer, because in some cases we haven't got the resolution to actually identify the vortex itself. On a couple of images, there's a small dark spot either to one side or in the centre, but it's difficult to ascertain. But I think certainly this image probably indicates really what was going on. It's again by Dave Tyler. We've got this large circular image, which is probably the vortex, and it's surrounded on its following edge by this darker material. So depending on the resolution, we either saw it as this elliptical thing with the vortex inside. Looking, obviously, we can't get this resolution. These are images taken by the Cassini spacecraft that shows the vortex. And in fact, actually, if you look at this, the vortex shown with these arrows here, here, and here. Over time, it's actually shrinking. So it would seem that in the amateur images, we're seeing this sort of elliptical cloud structure around it. Sometimes it was central and sometimes to one side. But I think it's good that the amateur images even picked this up. But this was certainly the major feature, one of the major features near. And this is a colour-coded image because the imaging system on Cassini had a filter set. And this was done with various filters which would try to estimate the altitude of various features above the sort of base cloud layer at the base of the troposphere. This is obviously the head of the storm. And wouldn't it be great to get this resolution with a 4-inch refractor? It'd be fantastic. I wish we could do this. But as we said here, the plasma wave experiment picked up radio emissions, which are indicators of lightning. And virtually from the 5th of December, it was the bolts that they were picking up were virtually continuous. In fact, I've seen some of the professional papers where they say that the energy expended in the lightning in this storm was almost about 80 or 90% of the total energy budget they expected from the planet. And picking up lightning is going to be difficult, but this is actually a daylight image showing a huge lightning bolt, and that's the picture about 30 minutes later where it's gone. So these lightning bolts must have been absolutely huge and dramatic. But interestingly enough, the lightning, the measurements from the plasma wave experiment curtailed about August the 28th, which might indicate a date when the storm actually abated and came to an end. But towards the end of June, the plasma wave didn't pick up any lightning, and for a few days there was no lightning recorded at all, and then it reoccurred again at a fairly low level, which indicates that something interesting happened towards the end of June. In fact, all the professional observers indicated that when this head collided with the vortex, or got to the same longitude of the vortex, the head came off worse and was destroyed. We can see what was happening by, this is a plot of the longitudes measured by lots of images and drawings of the position of the vortex and the head of the storm in what we call System 3 longitude. It's a frame of reference against which we can measure things. And we can see that both, oh, sorry, I've jumped ahead. I'll just go back. Always do this. We can see that both were sort of drifting with increasing longitude over time. The head, which is marked by this dark line and the circles, was drifting much faster than the vortex. So eventually, by the end of June, their longitudes were almost similar. The measurements of the head of the storm are pretty good, actually. They almost fit the best fit line, whereas the ones of the vortex are a little bit more scattered. This might be partly because of where we thought it expanded and measured the centre, it was incorrect, and the measurements should have been a little bit more towards the preceding end. But also there was suspicion, even in the professional papers, that this vortex motion in the atmosphere sped up and slowed down a little bit. But certainly the two came into contact towards the end of June. What happened after that is difficult to ascertain, but certainly there seems to be something in the amateur images which indicates the vortex not far from the predicted position where it may be. Before I look at some of the amateur images of this collision, it's interesting to look then lines that I generated, how they compare to the professional results. In the BAA observations, we get 2.81 degrees per day for its drift, the storm head, and just over 0.8 of a degree for the vortex. And these are the professional results, and I'm pretty pleased they're very close. And in fact, the professionals probably had access to more amateur images and professional observations than we do. But what happened with the collision? During the opposition was at April, and these observations were moving, and Saturn was below the celestial equator. So in many cases, it's starting to move towards the sun. Here in northern temperate latitudes, it's getting into the twilight, so observations were a bit more difficult to make. But here is an observation by Martin Lewis, great imager here in the UK, and what it shows, that's the head of the storm, and that dark area is the vortex where they're starting to come together. The red line points to the vortex, the white line points to the head of the storm. Over the next few weeks, there were very few observations, apart from two who made very important observations indeed. First of all, Trevor Barry in Australia made a lot of observations over this period, and also a guy called Paul Maxson in the States who observed on virtually every night in June, although the longitudes he covered weren't always off the centre of the storm. And this is by June the 12th, and you can see that the head and the vortex are coming very close together, and even suspicion of some bright material there. There's a number of bright spots a bit further south. By the time we got to June the 18th, it's difficult to know what is going on. Is that the head of the storm and that the vortex, or has something happened to both of them and we can't see them? The last decent image of this area, taken again by Trevor Barry, shows something there which is near the predicted position of the vortex, and a bright spot there, much further south than we would have expected the head of the storm. So these amateur images also indicate something interesting happened to this storm and their collision. Although there were observations made after this, often as not, they either didn't cover this particular aspect of the planet, this longitude, or the scene was so bad the resolution was good. Although I'm really impressed with all these observations, part of me said, wouldn't it be great to have another night showing this area, or maybe 2 nights, or maybe 3? But I think this is showing the end of the head of the storm. But what does Cassini show? Well, there's the head of the storm, and there's this vortex. And by certainly July, only the vortex is left. So the head was completely destroyed. Our observations show something happened towards the end of June. The professional observations show something happened at the end of June. So it's quite an important thing for this study of such storms. Some professional papers indicated that, some professional papers indicated that both the vortex initially disappeared, but that's not the case. There's lots of observations after that, and I'll come back to that in a moment. But if I may, I'd like to just move away from the 2010 storm and talk about these great storms as they've occurred over the last century or so. The first observation of one of these was in 1876 and shows a bright region in the equatorial zone. This was done by an American observer, D. Julia Edgecombe. We then had one in 1903 by the great British planetary observer, W.F. Denning. And of course, the classic one that everybody knows about is the observation made in 1933 by Will Hay, who was a musical and film comedian, showing this huge white spot. Interestingly enough, I'm not sure if it's still there, but Martin Moberly wrote a really excellent appreciation of George Olcott. It's well worth a read of his experiences with George Olcott and what George Olcott did for amateur astronomy. And Martin notes that a few days later, I think it's either 2 or 3 days, George Olcott, using nothing more than a 4-inch refractor, independently discovered this. And I think that's a nice tie-in to this talk. After that, one was seen in the Pic du Midi in the north temperate latitudes, and then we move on to 1990, which was observed by Hubble, and now in 2011, this observation again by Dave Tyler, showing aspects of all these 3 great storms. I'm sure all of you have noticed something straight away. First of all, very, very roughly, these storms are separated roughly by 28 or 30 years or so. Apart from this one, I'll come back to that in a minute. So it seems that every one of these storms only occurs once in a Saturnian year. The other thing I'm sure you've all spotted is that they seem to change latitude. We've got one in the northern equatorial zone and then in the mid-northern temperature area, one in the northern equatorial zone, one quite high up in the northern hemisphere, one in the northern equatorial zone, and one in the northern temperature latitudes. So there does seem to be this alternation. Whether there's something indicating something happening below the planet, I don't know. But this is something that has to be accounted for by when theorists are trying to look at these particular features. Interestingly enough, if we look at when these things occur, another interesting thing about this is the number of days from the northern hemisphere spring equinox, and that line marks where the autumnal equinox occurred. And you can see that all these generally appear to appear in the northern hemisphere autumn. The 2010 one is the exception. Nobody really knows why this is. Indeed, after the 1991 occurred, because of this sort of rough Saturnian year prediction when the next one was going to be, many people predicted that the next one would occur between 2017 and 2020. But this one occurred in 2010. This sort of pseudo-periodicity has been something noted by quite a few people in various papers. But if you want something easy to get at, there's an excellent article on the periodicity of these storms by our very own Dr. Richard McKim. And it's in this edition of the journal. And in this, Richard, as Richard normally does a lot of research and things, he's actually found some drawings of some of the earlier storms that have never been published, which in itself is interesting. We also observed something unusual, that these storms seem to be separated by about 57 years. So the ones between the equatorial zones were about 57. The ones in the northern hemisphere, high northern hemisphere, about 57 years. And he noticed that the 2010 one was a bit unusual. And Richard had actually found an old BAA circular which indicated that maybe a New Zealand observer had picked up a large storm in 1953, which would fit Richard's idea of different latitudes occurring, storms occurring at different latitude bands every 15, 70 years or so. However, Richard has received these observations relatively recently, and he's had a look at them, and I've had a look at them, and I'm sorry to say that I don't think they're all that convincing, unfortunately. So Richard's idea of the recurrence every 57 years is probably not right. And I know in discussions with Richard, he's going to either write a paper or a note or something for the journal, summarising how these observations didn't really indicate one of these big storms. But this pattern has to be fixed up, has to be explained by theoretical modellers looking at Saturn's atmosphere. What causes these storms? Now that is, here I'm on incredibly dodgy ground. And the sand is slipping underneath my feet because a lot of the atmospheric physicists have done modelling to try and explain this. We can think of the great atmospheric physicist Andy Ingersoll and some of his students and various other people as well have come up with ideas that try to explain what was going on. And I'm not really qualified enough to try and give the answers really in atmospheric physics, but all the various ideas seem to think that these storms, when they erupt, heat up the upper atmosphere of Saturn. Now, heat up, I'm using in the Saturnian sense and not the sort of temperatures that we'd expect on the Earth. It's warm in the atmosphere, so it's instead of really, really cold at minus 200 degrees centigrade, it's a little bit warmer, maybe at minus 80 degrees centigrade. These storms seem to bring up water, and the latent heat of water probably helps drive these storms. And indeed, water ice, as I mentioned earlier, has been picked up by Cassini in the body of this storm. And they think that the atmosphere gets saturated with water or perhaps other substances as well, like ammonium hydrosulfide. And these being heavier than the hydrogen that they sit in, eventually rain down out of the atmosphere, clearing the atmosphere, leaving it fairly dry and relatively warm. And a lot of the ideas are that the atmosphere cools down, but it takes between 20 and 30 years to cool down, to allow convection, violent convection to take place. But there's so many unanswered questions about this. These ideas may be right, this comes every 20 or 30 years or so, but some of the questions are, why don't we see them in the southern hemisphere? Why don't we see these violent convection in the southern hemisphere? How does it seem to vary between the equatorial region and the northern region alternately? Is this just that we're around at the time when this is happening? And I think that more work is needed to try and explain this a little bit more, but these theories may well be correct. But what happened after the storm hit in 2010? Well, certainly the storm died down. From our perspective as amateur observers, Saturn disappeared behind the Sun at solar conjunction and was sort of lost from sight. And many, when it reappeared then, the disk was almost featureless. How am I doing for time, David, just a matter of interest?
You've got 20 minutes.
20 minutes, oh, that's good. I'm almost there for questions. This zone became very bright, as we see in this end. But in this area, there was a few vague clouds picked up in some of the images, but it almost looked featureless, as if everything had been cleared out by this storm. And it's, you know, for the next few years, things got very quiet on Saturn. But I mentioned the vortex, and I know initially some professional observers thought it actually disappeared. It's still, well, certainly up until last year, it still exists. A number of vortices were seen at this latitude, but this is the one we're thinking about, and this was seen by the Cassini spacecraft in 2013. And this is a relatively recent observation made in last October by Trevor Barry. He's got a 16-inch telescope, and there it is again. And Trevor has made, he's got a very good piece of kit, he's got a very large telescope, the optics and mounting are superb. And of course, he's been in Australia where Saturn has probably been overhead, where it's been scraping the roofs in this country when it's up. And over the years, he's been tracking this feature. Sometimes it appears even fainter than that, but his observations all fit on the same track. So this vortex has lasted quite a long time. And why this is, well, I suppose that, you know, there's no solid land as such on Saturn, so they don't dissipate as things would do, low-pressure systems do on the Earth. There's an interest also, it also shows the North Polar hexagon. And because his telescope is so good, there's also other features that he's picked up as well, such as waves in some of the belts, bright features in the equatorial zones, and so on. So that's how it is. So when we'll get the next one, I don't know. But when will the next one occur? Well, as you've seen already, theoretical predictions for the next one have gone, it's like predicting the weather in this country. We don't really know. If we'd have gone at 1990 and maybe wanted to turn in 2017 to 2020, and add another 28 to 30 years to that, we're looking at late 2040s before the next one will come. And if there's a sort of the same pattern of 28, 29 years after 2010, we're looking at the late 2030s before the next one will come. But really, we don't really know. But if one does occur, it would be nice to have another spacecraft in orbit around Saturn, which could pick up the lightning bolts, the radio emissions from the light bolts, and prove that, in fact, it's another one of these great storms. So when the next one will occur, I honestly don't know. But that's why we keep on observing. That's why we keep looking. You know, things do change. But there are some things that can be picked up even now and maybe occur over the next few years. Over the last few years, the north face of the rings has been tilted towards us. The North Pole of Saturn has been tilted towards it, and so much of the southern hemisphere has been hidden. But now the ring tilt is getting less. More of the southern hemisphere is coming into view. And there may be two things to look out for if you've got the instrumentation. And obviously this is a great image by Damien Peach showing the storm with all the waves in it. But it's one of these features in the what we'd call the south equatorial belt latitudes. A number of these occurred in 2005, 2006, and then a lot of them dissipated. But there's certainly evidence in the section observations that these are can be relatively long-lived features. And this was one that was observed during the 2010-2011 apparition that seemed to fit the observations from the previous apparitions, indicating it was long-lived. So as the rings start to close up and we see more than the southern hemisphere, it'll be quite interesting, to see if this type of feature occurs in the mid-south equatorial belt as well. But the other thing is in a bit further south, in the mid-south temperate latitudes, and I mentioned that when not long after Cassini went into orbit, he discovered these radio waves indicating lightning, associated with some bright storms in the southern hemisphere. And here is an observation of one of these storms that occurred in the previous apparition in 2010, an image by Peter Garbert. And these storms just appear as bright spots, but the Cassini measurements indicated they were convection events and, excuse me, with quite a bit of lightning in them as well. So any theories that explain the great spots have also got to explain these as well. Whether we'll see some more of these things as more of the South Pole comes into view, we just have to wait and see. But this one, normally they appeared as just bright spots, but the 2010 one was interesting because several of the spots in there started to show brightening events, and also it started to expand in a sort of smaller way as the great white spots. And indeed, towards the end, in this image taken by, sadly, the late Peter Edwards, shows that it was expanding along in a longitudinal direction, and it reached nearly 30 degrees or so in longitude. And I'm taking a real punt here because I don't know really what I'm talking about, but this sort of mimics in its behaviour the rapid brightening, the expansion of one of the biggest storms that we saw in the Northern Hemisphere in 2010. So this again might be something to look out for if you've got the equipment as the rings start to close up. A large number of observers contributed to 2010-2011 observations, and they're all listed here. And certainly this talk would not have been possible at all without the observations provided by each and every one of these observers. Some made visual observations, some made imaging observations, some made imaging with specialist filters such as methane filters and so on. Some of these actually showed immense dedication because they made many observations throughout the apparition. And several of them, dedication beyond belief because the storm erupted in December, opposition was in April. So to make some of the observations meant either staying up very late or getting up early, and as it was Northern Hemisphere, often not in the cold, to actually make some of these observations. And certainly getting out of a warm bed and going out to the telescope in freezing conditions can tax any observer going on. So to each one of these, I like to thank. And as I say, a lot of these made dedicated observations. George Alcock, one of his characteristics, he was a dedicated observer. And I'd like to think that he would have appreciated the dedication shown by these observers in following this very notable storm. Ladies and gentlemen, thank you very much.
Thank you very much, Mike.
How have I done for time?
Yeah, we've got plenty of time.
Oh, good.
We've got plenty of time. We've got a few people watching on YouTube, only 13. None of them have asked questions so far. Any questions from the hall to Mike?
Yes, Nick.
I'll ask one. I'll wait for Mike. You don't need to
Mike with the mic. Mike with the mic.
So the total amount of solar energy that goes into Saturn's atmosphere is quite complex, isn't it? Because
Yeah.
it depends on where it is in its orbit, it depends on the ring tilt and all kinds of things. Is there any kind of obvious correlation between that and the incidence of these storms?
I don't know. Some professionals say it might be seasonal. In fact, on some of the professional papers I've seen where they've tried to work out the energy forming on the planet and when these storms occur. I think there's a guy called Sanchez Vega who's done a lot of work in this, and they're certainly trying to work out the energy falling on the planet. So, you know, and certainly when the Northern Hemisphere is towards us, it's at its Northern Hemisphere winter is very close to aphelion, furthest away from the sun. Whereas the Southern Hemisphere, it's very close to perihelion. So whether this has to be taken into account, I don't know. And I really don't understand some of the professional papers, but I'm sure they've taken the energy budget coming to the sun into account in assessing how the energy goes around inside the planet. Not on the exterior of the planet, I should say, not inside the planet.
Jim.
Thanks, Mike, for a great talk. Was there any evidence of enhanced activity of this nature at all in the sort of 2017 to 2020 period? Because it seems a very odd gap.
I say no, but they weren't big enough. But certainly, going on memory now, it's been a long day. But there were certainly features observed very close to the North Polar hexagon. There were some very bright clouds appeared there and some bright spots, but not on the scale as we see with this, which is a planet-wide disturbance. These were appeared in some of the more sophisticated, better resolution amateur images. And because Saturn was so far south of Saturn, so all the observers in Australia, etc., were able to pick these things up. But there was no obvious thing going on there. And as far as I know, there were no these radio waves that the plasma wave experiment picked. There was none of them as well. I expect to see an email saying I'm wrong, but I think that's how it went.
John Rogers.
Mike, I remember at the time of Oh, sorry. I remember in the Voyager spacecraft coverage in 1980-81,
Yeah.
there was a strange sort of ribbon, a
Yeah.
wavy jet stream close to the latitude where the Great White Storm of 2010 erupted.
Yeah.
I'm just wondering whether after 2010, a similar ribbon ever occurred. 'Cause I don't remember ever reading.
I don't remember ever seeing something about that, and I know what you say, but it's interesting to note that Richard had kindly plotted on them wind profiles that the latitudes where these storms occurred seem to be very close to peaks of the jet streams. And in fact, some of the professional observations that were made, we couldn't see it as amateurs because it was near the sun, but Cassini picked up something they called the string of pearls. And it seemed to be a lot of dark spots, or I think there were dark spots in infrared, and the storm erupted near one of them as well. So there's some interesting things going on which we probably don't understand. Paul. Dr. Paul.
Thanks, Mike. That was an excellent talk, by the way. It's always nice to see a Saturn talk. It's a wonderful planet to observe. I was just wondering, do we know how these storms get started? Cassini was there right when that first storm started. I remember seeing that there was an intense thunderstorm activity.
Yeah.
Do we know what triggers that? Because I don't know, and I've asked colleagues at the university, and they didn't know.
As I said, I'm probably the wrong person. When I alluded to what the theoreticians are saying, is that they think that the atmosphere remains stable, it dries out, and it cools down. And I suppose in Physics 101, you've got to be hot to cold, to get convection to occur. And they think eventually the temperature drops down, that it allows violent convection to occur. But why does it always occur at them sort of particular latitudes? Why is it not all over the place? I honestly don't know. I think you're asking the wrong person, maybe.
I've yet to find the right one to ask. Thanks, Mike.
Yeah, Mike, so how important are amateur observations to sort of being first to detect changes on Saturn?
I think they're very important. I think there's a lot of the amateur organisations around the world have their own people who contribute. So maybe in ALPO or some of the other organisations, there may be additional images that show up. There's a virtual VPOL, Virtual Planetary Observing Laboratory, where some amateurs send the very high resolution images. And often as not, if you trawl through some of the professional papers, they cite some of the amateur images in these because they, Cassini's not always there. They don't always have the telescope time. And one thing amateurs can do, they've got temporal coverage. We can observe when we want. And certainly in a lot of the papers I've seen covering this on the professional papers, they do show amateur images. Obviously the really good ones, but they do show amateur images. So I think it's important. You never know. It's like anything in astronomy. When you're looking for comets, variable stars, the sun, something interesting might pop up when you're observing. And that's half the fun of what we do.
We were very fortunate in having Cassini there at that time when that storm erupted so spectacularly and so many amateurs were able to image it as well. But of course, Cassini is no more. It's disappeared into the atmosphere, so you're on your own now. You've got to keep watch on your own account.
And I'm again on shifting sand here. I mean, Hubble will get decommissioned at some point. We've got the James Webb, which seems to be going well. But I think through John, we heard a talk quite last year where they were talking, Lee Fletcher was talking about amateur observations of Neptune. What I didn't realise at the time is the field of view of the Webb telescope could encompass Uranus and Neptune, but it'd be a tiny thing on Saturn or Jupiter. So they have to take lots of montages to see things. So whether it'll get the time to look at the planets. So I think, across all the planets, it's well worth observing and looking at because you never know. You might see something unusual.
Yeah, I think they probably will look at the planets occasionally.
Sorry, my voice has just
This isn't the same vortex by any chance being given an energy kick every Saturnian year, is it? By any chance, it just comes back to life.
I don't know. Were we thinking of the polar vortex or the... I honestly don't know. I'm afraid I can't answer that question.
Well, there may be several at different latitudes, several different vortices that we can't see normally.
Yeah, I mean, certainly the Hubble Space Telescope images the giant planets and probably all the planets every so often. John probably knows a lot more about this than I do for Jupiter. And they have this ongoing program where they take Hubble images, and certainly some of the things I've seen, they have actually picked up small vortices on Saturn in addition to the one discussed today. Anything else?
Presumably it gets warmer as you go into Saturn.
Yeah, yeah.
So it may be there's more activity. It may be in the lower levels, it's more like Jupiter looks in reality.
Yeah.
But we don't have any way of observing that at the moment.
No. I'm sure, again, I'll look to John for confirmation of this. Some of the results of Juno going around Jupiter and looking at its gravitational field and its interior, I'm sure there'll be a lot of read over to Saturn.
Yes, and the last days of the Cassini mission enabled it to probe Saturn's interior, somewhat like Juno is probing Jupiter's interior.
Yeah.
And in fact, they're very similar in terms of the depths of the atmosphere, the depths of the jet streams.
Yeah.
But yeah, I mean, indeed, Hubble observes Saturn as well as Jupiter about once a year, and there's no indication of lasting disturbances that are likely to persist until the next great white storm appears. And likewise, Cassini, I think, as you mentioned, it observed the string of pearls. There was a series of little thermal features in the latitude in which the great white storm erupted, but there was not a single feature which seemed to be its precursor.
No, they couldn't put it down to
one of this string of pearls.
That one is the cause of the storm. But I think, as you see, the amateur observations, I think we've done pretty well. I think the coverage that, certainly in the BAA section we've got of this storm, I'm well impressed with and very, very pleased about.
I mean, since I've been kindly given the microphone, could I comment also about the PROAM collaboration that you were talking about? Trevor Barry in Australia was really a formal collaborator with the Cassini plasma wave science team. They were the ones who were detecting these bursts of radio waves, plasma waves, initiated by lightning. And so they would collaborate with him continuously. So whenever they observed bursts of lightning, they would ask Trevor, is there a white storm visible in that latitude on Saturn in your images? It was an excellent collaboration.
Yeah, and I mean, Trevor's lucky that he's got the kit, and he's got, at a reasonable latitude, we can follow all the planets around. But these images, every time I open my inbox and there's a set of images from Trevor, it's usually, gasp.
Yeah, we have BA members all over the world making these observations, including in the southern hemisphere, which is very useful since Saturn is in the south for another 10 or so years. That's very interesting. We're clearly at a very early stage of Saturn atmosphere studies. There's a lot more that we don't know than we do know. So it's an opportunity for everybody to contribute to that. Thanks again.
Thank you, David.
Our next speaker is Hugh Allen. Hugh is an industrial chemist with a career in the printing industry. He studied, before they did that, he studied natural sciences at Cambridge. His interest in astronomy started in 2008 when his wife bought him a telescope. Unusual present for a wife to buy the husband. He started observing with it and they started doing astrophotography, but in the last 8 years, spectroscopy has been his main focus. And he has a passion for this. He shares this in talks and courses. He's also chairman of Wells and Mendip Astronomers and a member of the Herschel Society in Bath and, of course, of the BAA. So Hugh is going to talk to us about observing the 2017 to 2019 primary eclipse of VV Cephei in a low-resolution spectroscope. So, Hugh, I'll hand the podium over to you.
So how do I get
Hopefully hit escape and it should disappear.
Escape and disappear.
It's escape? I do it. Yeah, go on.
Sorry about that, Kit.
No, that's all right, mate. No problem.
That's the one, isn't it? That's it.
Yes, thank you for getting through that very long title, David. Yeah, just to start by saying thank you very much to the BAA for inviting me to speak. And I know I'm just a follow-up act to you, Mike, but I actually also feel honoured to be speaking in front of the BAA. So yes, observing the 2017-2019 primary eclipse of VV Cephei in a low-resolution spectroscope. These are the sorts of things I'm going to be talking about. And I chose this image from a sort of a paper written in Austria about a school observing VV Cephei during the eclipse. And I thought this was a rather nice astrophoto of VV Cephei, really a very beautiful red star. So I'm just going to make a few opening remarks, if you don't mind. I'll then introduce the star to you all and describe a little bit this observing project and show you as well some of the properties of this binary system that I was able to deduce from the data we collected. I mean, you gave a very nice introduction, David, so I'll skip over some of this. But yeah, I live in, I don't know how many of you know Wells in Somerset, but rather beautiful city, actually, smallest city in England with a lovely Gothic cathedral. Recommend you come and visit Wells if you can. I am an industrial chemist, as you said, David. I work in the inkjet ink industry, actually, in Midsummer Norton, near Bath, where I'm a development chemist working on the development of inks for industrial inkjet printers. Astronomy isn't my only passion. I also play a lot of badminton. In fact, here I'm about to serve to my wife, and I can't actually remember who won this rally because she's a pretty good player as well. I'm chairman of the Wells and Mendip Astronomers, as David said, and we meet a lot in Wells, but we also observe all over the Mendips. It's really quite a nice dark sky up on the Mendips. And in the last, 8-9 years, my sort of passion in astronomy has been spectroscopy, probably linked to my work as a chemist and in cover. And that's just a sort of presentation I put together for some of my talks to show some of the spectra I took over the last year or two. And I think it shows quite nicely the beautiful different forms that spectra can take of different stars. And this gentleman on the left, actually this is a link to the former venue of the BAA in Burlington House. When I was there for a talk a couple of years ago, I sneaked upstairs during the break and I didn't know it was there, but I found this portrait of my spectroscopic hero. And he was one of the pioneers of spectroscopy in the 1860s, William Huggins. And he wrote this in his essay on the new astronomy at the end of his career. Spectrum analysis could not fail to have a powerful influence on the future of astronomy. And of course, he was right in professional astronomy, but maybe not so much yet, although it's a growing field in amateur astronomy. And that's one of the reasons why I love to give talks. I try and kind of introduce spectroscopy, demystify it a bit, and show that it isn't perhaps that frightening. Actually, one of the nice things in Burlington House was on the opposite side of the doorway from William Huggins' portrait is the portrait of his wife, Lady Margaret Huggins, who wasn't just his wife, if I can put it that way. She was also a genuine collaborator and particularly helped him in the use of photography in spectroscopy. So she's there too. And I ask this question when I give talks about spectroscopy. What does spectroscopy mean to amateurs? Because I think it is a little bit frightening, technical, whatever. I think you do produce genuinely beautiful images in spectroscopy, which I hope you'll see during the talk. It is, in many ways, just a way of observing the sky, which, again, I hope you'll see. And of course, if you want to, you can get into the astrophysics and you can do your own science and detective work and contribute, as Mike was talking about with Saturn observations, you can contribute to professional astronomy as well. This is the kit I've used to take the spectra and is also similar kit used by other contributors of spectra to the project. It's the Alpi spectroscope. This, if you like, is the heart of the... Is that working? Doesn't seem to be. Oh, no, it's that one. There we go. this is the mirror slit, which is here in the spectroscope. And of course, by having the slit cut into an angled mirror, it allows the light that comes from the telescope here, this is an 8-inch Meade LX90 that I use, the light passes through the slit, which gives you the resolution in the spectrum. But of course, in the mirror, your guide camera can see the field of view, so you can actually point the telescope at the right object and keep it on the slit. I have a focal reducer to match the optics in the spectroscope here. This white box contains 2 lamps. One is a tungsten lamp for doing flats. And yes, you do flats in spectroscopy, just like astrophotography. And it also contains a neon argon calibration lamp, because the science camera here, it's a cooled CCD camera. It's mono for the best sensitivity. Of course, if you have a calibration lamp, which you take a spectra after every observation, you can calibrate the exact position of the spectral lines in your unknown object on the camera sensor. So that's a little introduction to the ALPI spectroscope. And of course, this talk is all about a paper that I had published in the Journal of the BAA last August. So if you want to know a bit more background and a few more details, please go online and take a look at the paper. So let me introduce VV Cephei to you. Here's the sort of field of view you find VV Cephei. It's pretty much in the center of the constellation Cepheus, of course, just ahead of the perhaps more famous constellation Cassiopeia. And of course, some of you will probably realize this makes it's a circumpolar constellation. So VV Cephei is actually observable pretty much all of the year. In fact, I think this view is pretty much what you get around this time of year as it starts to get dark. So VV Cephei is almost, if you like, at its lowest point, but it never gets lower than about an altitude of, I think, something like 25 degrees. And there it is. And whilst we're on this field of view, I just want to show you one other star, which is this one, Nu Cephei. And when I give talks about spectroscopy, I kind of liken spectroscopy. It's a bit like the opposite of supermarket economics. You know, in supermarkets, although you see it less these days, 2-for-1 offers. I'm afraid in spectroscopy, it's 1 for 2. Because in order to correct the appearance, the shape of the spectrum of your target star, you have to take the spectrum of a calibration star, a reference star, nearby in the sky. And I chose Nu Cephei to correct all of my spectra, so I'm just showing you that there. And in fact, this graph here shows you why you need to do this if you want to get the maximum information from your spectrum. So you can see the uncorrected spectrum, so straight out of the software, if you like, from the images in the camera, looks like this blue spectrum. This is a VV Cephei uncorrected. And if you correct it using a reference star, then you get the true shape of the spectrum. So it's quite an important process in spectroscopy. So let me tell you a little bit about VV Cephei and its sort of background, if you like. So this paper in 1969 placed VV Cephei as the sort of principal star in a really quite a rare class of stars known as the VV Cephei stars. These are supergiant binary systems whose spectra show emission lines of hydrogen. And the primary star is always a K or M type, so quite a cool supergiant, while the secondary is generally an early B-type star, so a very hot star. And you can see VV Cephei listed here, one of only 13 members of this rather exclusive group. And here's a spectrum that I took only a couple of months ago of VV Cephei. And you can see it has the classic shape of a cool red star. And you see I've marked the band heads of the titanium oxide absorption bands in the spectrum. And this is very typical of a low temperature star. The temperature is low enough, about 3,500 Kelvin, for it to express absorption of molecules in the atmosphere. So a very typical spectrum of a cool red star. And I've also marked, hopefully you can see them, the position of a hydrogen Balmer lines, and you can see the intense hydrogen alpha emission, hydrogen beta emission here, even higher energy Balmer lines are visible. And this is the spectrum you see for 18 out of 20 years. And this spectrum, just to give a bit of history, to put it in context, this spectrum was first observed by Annie Jump Cannon. And she published this paper in 1912, classification of 1,477 stars by their photographic spectra. So, of course, these were prism spectra, and she was one of the sort of Harvard computers. In fact, she led the Harvard computers for many years and developed, of course, the stellar classification system we now know. And here is the entry for VV Cephei here. And there's actually a note, a remark, 155, and if you take that out of the paper, here it is. The spectrum of this star is of the third type, so it's a cool red star. And on the 27th of November 1979, the hydrogen beta line was bright. And then she notes that on a photograph, a particular photograph, many of the hydrogen Balmer lines were bright. Note, though, that she doesn't talk about hydrogen alpha, and we'll mention this in a minute, because, of course, these photographic plates were blue sensitive, and I think, really, there was relatively little sensitivity to the red light, the red end of the spectrum. And, of course, these were prism spectra, so it's the blue end that's most spread out and most usable from these prism spectra. She also notes, by the way, that this was a variable star, and she actually measures the magnitude off a number of plates with a variation of about half a magnitude. So the first sort of in-depth academic paper about VV Cephei was written by Sergei Gaposchkin in 1937, where he showed for the first time that this was an eclipsing binary. So we noted from that 69 paper, this star is like the prototypical star for the VV Cephei stars. All these are supergiant and hot star binaries. But we're lucky that VV Cephei is an eclipsing binary. The plane of the orbit is almost edge on to our line of sight. And what I enjoyed about this paper was particularly that it used the work of Annie Jump Cannon to sort of inspire, I think, Gaposchkin to do this study. And Annie Jump Cannon sent Gaposchkin a sort of review of all the spectra taken at the Harvard Observatory. And she wrote, the spectrum appears on 21 photographs taken between the years 1887 and 1927. The star was classified as MAP, so a cool giant star, M. The peculiarities being as follows: bright hydrogen lines, decreasing in intensity from H beta to H zeta. The spectrum extends into the violet as far as spectra of class B, so an unusual observation. The exceptional appearance of the spectrum occurs on a photograph taken on September the 24th, 1895. The spectrum was then of a normal class M. The violet region is no longer seen, shorter than the H and K calcium lines, and the hydrogen lines are not bright. So she'd already got this hint that there's some periodic change in the spectrum. So I just took two of the photographic images, single images of spectra of VV Cephei during this study. Two of the spectra that I took, one on the 19th of May, 2018, pretty much at the center point of the eclipse, and another one later on the following year outside of eclipse. And you can see how the outside of eclipse spectrum is much brighter. This is the blue near UV end of the spectrum. This is the red near infrared end. You can see how much brighter the star is in the blue near UV outside of eclipse than in eclipse. And of course, indeed, as Annie Jump Cannon said, these emission lines have disappeared in the eclipse spectrum. You can actually, doing this careful response correction, so carefully correcting the shape of the spectrum for effects of the instrument and the atmosphere, you can then sort of build this picture of the onset of the eclipse in the color, the shape of the spectrum. So you can see the spectrum starts on June the 3rd, just as the eclipse or just before the eclipse is beginning, and gradually the intensity of blue light in the spectrum is decreasing. So you're seeing the disappearance of the hot blue star behind the red supergiant. but it's actually very gradual. You know, you're talking here over 6 months, 6 to 9 months before the blue light from the hot B-type star has completely disappeared. And already this gives you a kind of hint of how tenuous these red supergiants are. This is not an abrupt edge like the sun. This star, the blue light from this star takes a number of months to disappear. So we now have this model of the system. It's pretty uncertain, actually. I mean, we're 160 academic papers later. And because of the variability of the red supergiant, its tenuous atmosphere, its distance, and so on, it's not entirely certain some of the parameters of the system. But using the latest parameters summarized in this study here, in the lead up to the eclipse that I observed, I just built this model based on those parameters out of an online binary star orbit sort of simulator. And you can see the hot blue star is here. Actually, this isn't quite to scale. It would be even smaller than this relative to the red supergiant. And you can see the eclipse happening. It just almost just brushes the top of the star. So the latest understanding is both these stars actually have a similar mass, 20 times the mass of the sun, roughly. So they'll both end their lives in spectacular supernovae at some point. And this orbit takes over 20 years to complete. And we're lucky because the hot star carries this equatorial disk of material that is accreted from the wind from the red supergiant. And in the intense UV light from the hot star, this is where we get the generation of these emission lines that you saw in the spectrum a moment ago. And of course, that means that the eclipse can be observed spectroscopically by the fading of these emission lines. Fortunately, I've sped that orbit up. We don't have to wait 20 years. So here's just a movie I did of just the spectra that I captured with my spectroscope over the 2 or 3 years, if you like, it took for this eclipse to happen. So on the left, you just see this movie unfolding. The green spectrum, when you see it, is the very first one I took in 2016, well out of eclipse, before the eclipse happened. The red spectrum that you'll see appear is the spectrum that was actually very near the eventual center point of the eclipse. And then I just lined up all the eclipses here, running from the earliest one to the latest one. And you see, here's the hydrogen alpha emission, and you see it fade. I don't know if you can tell from where you are, but actually it never fades completely, and you see that in the spectrum here. This emission line is always present, albeit faded, during the middle of the eclipse. And then the accretion disk re-emerges, and you see the hydrogen alpha line brighten. The beta line is a little more difficult to pick up. There it is. It fades, and then it reappears here. So this eclipse, totality, if you like, lasts well over a year. So that's just a nice little movie to show it happening in time. So Gaposchkin wrote, "The variable star Vivi Cephei is an eclipsing system." And I actually pulled this out from his paper. I thought it was quite nice. He wrote, "During the last 12 years, so prior to his writing the paper, a considerable number of visual observations have been made by members of amateur observing societies, and the light variation is irregular, as Annie Jump-Cannon has also observed." So I just plotted the data for the visual magnitude of this star from the AAVSO database between June 2015 and May 2020. And these are the visual magnitudes, and indeed it is quite irregular. That irregularity and the fact that in terms of brightness, it's the hot blue star, the disappearance of the hot blue star, that's most contributing to the magnitude change. I mean, I don't know, can you pick out the eclipse there? It's not very clear. It is there, it's kind of, the mid-eclipse is somewhere around here. But of course, in Gaposchkin's day, it was photographic plates, these blue sensitive photographic plates that were used to measure the magnitude of the eclipse. So he was actually, if you like, mimicking in a way what we would now do with a B filter. So if you take the AAVSO B magnitudes, you see the eclipse much more clearly. And of course, Gaposchkin, when he wrote his first paper on the eclipsing binary, he actually says there he had access to 2,736 photographic plates. So he was actually able, in that time period, to pick out 3 minima like this. And they were nearly equally spaced in time, proving the star to be an eclipsing star. And he proposed a period of 20.4 years, with a period of totality of about 450 days. So here's just tabulated all of the eclipses that have been observed and the papers that have been written about the periodicity of the eclipse. And the interesting thing is, and I put the title of the relevant paper up here, the 1997-1998 eclipse, so the last one before the one that we observed, it was late, which is a strange observation. All of the previous eclipse matched the proposed period by Kokoschkin, 7,430 days, so 20.3 years. The very last one was late by about 50 days. And from what I've read, it's not entirely clear why this was, and it's been proposed, for example, was there mass transfer? If there was, that changes completely the masses of the 2 stars, much lower masses. So it's just another puzzle of this binary system. But nevertheless, the observation is clear. And when you look at the technique used to measure these eclipses, all of them were done with photometry, apart from one of the last ones, which was done with spectroscopy. So again, it was quite interesting to use spectroscopy, and maybe that would sort of uncover something different. But to use spectroscopy as a way of looking at this eclipse. So let's get on to what we did, observing this latest eclipse, and that's why it extends over such a period of time. You know, this is an event that lasts, yeah, pretty much the best part of 2 years, from first to fourth contact. Now, what inspired me to do this? Well, I mean, it was definitely a very well broadcast event on the internet and on spectroscopy forums, but there was this great paper written by Jeff Hopkins, Professor Phil Bennett, and Ernst Pohlmann in Germany. A campaign has been started to cover the 2017 eclipse of Vivi Cephei, I read in this paper. Not only that, but there was a section on the use of an ALPI, because often with these events, it's focused on high-resolution spectroscopy as the way to sort of understand really what's going on in these systems. But it did say use of an ALPI for low-resolution observations is encouraged. I thought, wow, that's interesting. It wasn't sort of that encouraged. It was, well, you know, there are some interesting absorption lines maybe, but I thought, well, it would be nice to show actually the potential, the power of low resolution. So these were all the observers who contributed. And you can see I've put this source here. I mean, I observed this star a lot. I made 69 observations for this study. But I encouraged a couple of people I knew actually through my Facebook sort of community, Jim Ferreira in California and James Foster in California. And they both directly submitted observations to me for this eclipse. And then the other observations I took from the databases, the online databases. Of course, the BAA has an absolutely fantastic spectroscopy database of great scientific value. And there's another database, ARAS, developed by some French spectroscopists. So I took the spectra from these databases as well to sort of fill out a little bit some of the gaps in the study. And this is the quote from you, Jeremy, here, because I thought this was really good. This was a paper that I think you had in the journal just recently. The importance of amateur astronomers maintaining a long-term record of a star's brightness, also contributing to a coordinated campaign. And I thought, applies to spectroscopy as well, of course. And so just drop the word brightness and put in the word spectra. And although this was a fairly loosely coordinated campaign, it does illustrate the importance of this idea of long-term campaigns and the science you can do from them. And this was the result. So the red points are the intensity of the hydrogen alpha emission line, and the blue points are the intensity of the hydrogen beta line. And these are the estimates of first contact as these lines begin to fade, second contact, when only in the case of the beta line, the emission completely disappears. The hydrogen alpha never completely disappears. third contact as they re-emerge, and fourth contact as they resume their previous intensity. So you can see the scale of this eclipse. I mean, it's odd, isn't it, why the alpha never disappears and the beta completely disappears. I think it must be due, I mean, hydrogen alpha emission, obviously it's a common target for astrophotographers. It can be very diffuse, and I think there are just regions around this system, maybe from the red supergiant wind, that continues to produce hydrogen alpha emission outside of the narrow disk area where the hydrogen beta emission originates from. And of course, from this observation, there's no astrophysics here, from this observation of emission line intensity, particularly with the beta emission, you can pick out very precisely the beginning of totality and the end of totality. Much more difficult with hydrogen alpha. I mean, both emissions vary in intensity, which is itself an interesting observation. But the beta obviously declines to essentially zero. In fact, it goes into absorption. So you can make a pretty good estimate of the eclipse midpoint, June the 3rd, 2018. So here, go back to that table I just showed you, but now I've put in a final column for the 2017-2019 eclipse. And here's the oddity. The period has returned back to near 7,430 days. So quite a difficult thing to explain, really. How can the period increase? And then based on the time from the center point of the last eclipse to my observation from this latest eclipse, the period has reverted back to what was originally observed. And I reproduce here, this was a sort of discussion that started on the forum. I know you were involved with it as well, Andy. You proposed a few ideas. But I just took this from a quote from one of Robin's posts, Robin Leadbeater. You know Robin, very, very well-known spectroscopist here in the UK, up in the Lake District. I have extracted B minus V from the AAVSO data, so if you like, the colour index of the star. And I've marked Hughes spectroscopic mid-eclipse, so that's here, this red line, and the expected values based on the earlier ephemeris. So, if you like, that's the 7,430-day period, and the measured ephemeris from the previous eclipse. And you can see that this midpoint actually pretty much corresponds to the spectroscopic midpoint. So, by two independent techniques, this change in period is real. It's not where it should have been. So, how about some of the other VV Cephei parameters? Well, you can make a rough estimate of the size of this red supergiant. I mean, I love the description of stars as supergiants, but everything about this star really is supergiant. So from the measurements of the second and fourth contact points in the eclipse, 536 days, you can make a rough and ready estimate of the radius of the supergiant, because spectroscopically the velocity of the stars has been well measured in the literature. I think it's about 38 kilometers per second, the combined velocity. So from the chord that the eclipse makes across VV Cephei, you can then relate that to the radius, the full radius of the star, and you get a radius of about 7.5 astronomical units, 1,600 times the radius of the sun. So I put here just a diagram of the solar system. In fact, it happens to be the appearance of the solar system yesterday. And if you put VV Cephei in the middle of the solar system, it would actually go sort of halfway out between the orbits of Jupiter and Saturn. So fortunately, Mike, Saturn is still visible, but I'm not sure we'd be there to see it.
John's got to be upset with you.
So it really is a supergiant. But as I mentioned, of course, these supergiants have very tenuous outer atmospheres, and we saw that really well, didn't we, in the gradual disappearance of the blue light from the B star. And you can do other science. So the mid-eclipse spectrum is no longer contaminated by this blue light. So it is the perfect opportunity to measure, if you like, the spectral type of the red supergiant. And you can essentially show that it's an M2 supergiant, so a class M early red supergiant. But if you compare that to a reference spectrum, so that's the brown spectrum here, you see that the red supergiant spectrum, the observed spectrum, which is the red one, is redder than it should be. And that's due to interstellar reddening. So there's gas and dust between us and the star itself that's reddening the light from the star. So in the software that you use to process the spectral images, you can use the same software to de-redden, if you like, the observed spectrum so it matches the reference spectrum. And you get a color excess of 0.35. And that's actually pretty close to what you find in the literature. So with careful response correction, using this reference star, this 1 for the price of 2, you can make pretty decent observation of this reddening effect due to interstellar dust. Now here, I don't deny, I'm challenging the resolution of the ALPI spectroscope. This would be much better and more accurately done at high resolution, but I just wanted to show that you can still make some estimate. You can observe, if you like, the fact that this emission line from the hydrogen beta emission line, shows the fact that this could be coming from a rotating accretion disk around the B-type star. So the orange emission is as the star is going into eclipse, and it's actually slightly redshifted from the at-rest value. And of course, if you think the accretion disk, like the star itself, is rotating anti-clockwise around the star, so once you've hidden the part of the disk that's coming towards you, then what you're seeing is just the emission from the right-hand side of the disk that's moving away from you, and hence the beta emission is redshifted. And then as it emerges here, this green line from the eclipse, the line is blue shifted. So the greatest shift is here just before these lines disappear completely. Here's the ingress emission just before it completely disappears. Here's the egress emission just before it reappears, or as it starts to reappear. And you get roughly, based on the Doppler shift, about 250 kilometers per second. And that, again, isn't far from the literature value for the rotation of this disk. Now, as I say, this is a pretty approximate stuff at low resolution, but it's nice just at least to be able to see it, even at low resolution. You can see it, that there's evidence that this emission is coming from a rotating disk. And this is further supported by the breadth of the emission line. In this case, I've gone to hydrogen alpha. So I've reproduced here by the red dots the intensity of the emission. So you see the eclipse, it never disappears completely, as I mentioned, and then it reappears. But if I measure the width of the emission line, what's called the full width half maximum, so if you like the width halfway up the intensity of the line, you can see there is evidence that the width is narrowing and then broadening again as the star goes into and out of eclipse. So again, this is evidence that the contribution of the broadening of the line from the Doppler shift of the accretion disk is disappearing, and all you're seeing here is the narrower emission from the more diffuse hydrogen alpha emission more broadly around the star, which of course is not in motion in the same way. So that's quite a nice supporting bit of evidence. You even see that the hydrogen beta emission emerges from eclipse before the hydrogen gamma line. And you can actually see this here. So these are the dates as the blue star begins to emerge from eclipse. And you can see the hydrogen beta line is not significant until the green spectrum. There it is. Whereas the hydrogen gamma line is here, already visible on February the 14th. So you can see, basically, what you're seeing is that these different energies of hydrogen emission come from different depths, if you like, of the disk. So the higher energy emission comes from parts of the disk that are nearer the surface of the hot blue star. So if you think about it, the first line completely to disappear is the high energy gamma, and then the first line to re-emerge is the lower energy beta. And this was actually first observed in the 1940s by Goedicke. This is a plate from his paper, and although it's rather full of emission lines, you can see here's the gamma line here. So this is a nice illustration of these sorts of photographic plates, and this is the hydrogen delta line here, emerging and re-emerging, and one is just ahead of the other. There's actually also emission from iron, which again is thought to come from this wind that surrounds the system rather than from the disk itself, and it never really fades. As you can see, these are the iron emission lines. So spectroscopy can tell you all sorts of things about what's going on in this system. So this actually is taken directly from the conclusion that I wrote in the paper, and I've just sort of picked out some of the things that low resolution observation has been able to highlight in this really quite beautiful but rather enigmatic star system. So what we showed was that this star returned rather strangely to a near 7,430 day period between eclipses, in line with all the previous eclipses except the last one. We were able to show interstellar reddening with a color excess of 0.35, very much in line with what you find in the literature. We made a very approximate estimate of the radius of this supergiant, 1,600 times the radius of the Sun, and also with an approximate estimate of the speed at which this accretion disk of that gas is rotating round the hot blue star. And I make the point that this was based on 4 years of amateur observations, so you definitely need to be patient, but also you can see the rich fruit that you can get from this kind of long-term observation. And it was very much a collaboration between several observers and also using the data from these spectroscopy databases, and this is just an illustration of their value. And I make this point as well. I mean, when I started this journey in 2016, I was only really 2 or 3 years into my spectroscopic journey, if you like. By the end of it, I'd learned a lot more about the control of the technique, about my understanding of how it all worked, and yeah, very much honed my skills. So it was absolutely fascinating project for me from that point of view. So I hope that I've convinced you that don't be frightened of spectroscopy. I believe it does produce beautiful images. I mean, you know, this is again the spectrum of VV Cephei outside of eclipse. You see these beautiful bands from titanium oxide. Here are the emission lines, hydrogen alpha, and you can just about pick out hydrogen beta here. You know, it's got all the things that I think, and I remember it was a famous astrophotographer called Adam Block, who I read a few years ago on Facebook. He said, you know, what makes an image beautiful? Pattern, shape, information. And I think all of these things are here in this spectrum. And it is just a way of observing the sky. You know, there's no astrophysics in here. Of course, there's a development of the technique, the use of software, understanding the correct way to process the information. But essentially, this is just an observation of a celestial event using spectroscopy rather than using photometry or visual observation. But of course, if you want to, you can go into the astrophysics, dig further, and actually make proper scientific observation. And thanks for listening.
Thanks very much, Hugh. Okay. It's nice to have both main talk of the BAA meeting by active amateur observers doing practical work on very different targets. Jeremy has a question, comment.
First of all, to say, Hugh, what a superb piece of work. I think that's absolutely fantastic, and a beautiful accompanying paper as well. Great to see that in the journal. So My question is, well, actually, it's a bit churlish because it may ask about the quality of your observations. So I noticed in the video, it wasn't always a smooth change, and I think you can also see that in your graph here. Is that noise in the system, or are there actual physical
No, that is
changes?
real. That is, I mean, there is an error, but I mean, I think I estimated in the paper it's something like 5 to 10% is probably the error of the measurement of the intensity of these emission lines. But this kind of variation is way beyond that, and it is real. So these emission lines really are varying quite significantly from one observation to the next.
And so do you know physically what's going on there? Is this something to do with the accretion disk? Do we know anything about that?
Yeah, I mean, I don't know for sure, but at high resolution, so the observations made in the high resolution campaign, Ernst Polman has published a couple of papers based on those bits of data, and he's suggesting that there's a sort of tilting, periodic tilting of the disk like this. I think with the frequency of observations his group made, I think they're suggesting a period of something like 42 days. So as the star is orbiting around the red supergiant, there's a sort of periodic tilting of the disk like this around the hot blue star, and that changes the intensity.
Amazing, you can see that.
Yeah.
So, and regarding the supergiant, is there any evidence that that's pulsating, or have people compared the width of the eclipse from one eclipse to another to see whether it changes in size?
Yeah, but I mean that's a good question, and could that be at the origin of this sort of discrepancy in period? You know, that there's actually a change, if you like, in the ruler. Yeah. I don't know is the answer. I don't know. I mean, in the papers that were published on the 1997-98 eclipse, one suggestion was there was actually a rather large mass transfer, and so it was a genuine, if you like, physical event. But I think that for that to happen, my understanding was that meant that the actual mass of these stars had to be quite different from the mass that had previously been estimated. You know, they should be much lower mass. So I don't know. It wasn't entirely clear to me how solid, if you like, this sort of explanation was.
Yes, and the fact that it's gone back to where it was before.
And the fact now that it's gone back to where it was before. But it's gone back to where it was before based on the late midpoint of the last eclipse. So, you know, it's difficult. It's difficult.
Super, thank you very much, Hugh.
Do we know, are there any other eclipsing binaries that have periods that have been observed to vary? Have you heard of any others?
Of this nature, no.
I mean, are we sure it's really the period that's varying, or is there some change in brightness in the system that is skewing the observations at that point a little bit?
Well, as I say, this debate started, didn't it, Andy, on the forum? It sort of petered out, but there, I mean, I don't know, Andy, if you have any sort of theories. I know you suggested...
I need to go back.
Yeah, sure. I think your head's more full of other things, isn't it?
But yeah, no, it was and so fascinating presentation, really excellent work, Hugh. I do have my own question, if I may, which is from your observations of the emission lines, were you able to get an estimate of the kind of the width of the disk, the accretion disk? Putting you on the spot there.
I didn't make an estimate of the width of the accretion disk, but I suppose in principle it should be possible from the shape, if you like, of the.
And I was wondering kind of the timing of the different disappearances.
Exactly. Yeah, those contact points. So yeah, no, it's
just thought.
Yep.
John Rogers.
Yeah, my question was really related to that last point. I wondered how much of this fading as you go into the eclipse and out again is due to the extended atmosphere of the red giant star, and how much is due to the extension of the accretion disk itself? Have you any idea of their relative sizes?
Yeah, you'd have to untangle those two things, wouldn't you? Because it's quite complex. Because absolutely, you saw from the gradual decline in the contribution of blue light to the spectrum that the outer atmosphere of this red supergiant is extremely tenuous. So yeah, I guess you'd have to find some way to untangle these two effects: the disappearance of the line. And,
there's definitely both involved.
Both are involved, yeah, absolutely. Yeah, both are involved.
I'm going to put in a plug for Barbara Becker's wonderful biography of William and Margaret Huggins, if you want to know more about the history of it. She started off writing a biography of William Huggins and then realised his wife was just as important to the story of it. So
Absolutely.
Really worth reading.
Yep. I would second that. I think I would love to have had a beer with William Huggins because I'm sure his passion for spectroscopy. I feel, I'm not trying to liken myself to William Huggins, but he was so excited. He wanted to do and observe and measure all sorts of different things, and that's exactly how I feel.
I was going to ask, wouldn't the existence of an accretion disk imply some sort of mass transfer going on anyway?
Absolutely, I guess it would, and from what I've read, the material in the disk probably comes. I think the physical separation of the two stars means that there's no sort of direct transfer of material from the atmosphere of the red supergiant onto the B-type star. But I think it suggested that the material comes from this very powerful wind from the red supergiant, and that's what then gets accreted onto the disk of the B-type star. Yeah, whether that kind of mass transfer is significant enough, I don't know. I'm not an astrophysicist, I'm a humble chemist, but from what I understand, what they wrote in the 97-98 paper, this had to be a much more significant event, I think, of mass transfer, yeah, which completely changed almost the parameters of the system.
Yeah, I was just going to say, actually, following on from that, presumably these stars were formed coevally as a binary. And I think in the table you put up earlier, the B star is a main sequence star.
Yeah.
So the red supergiant must have been much more massive to begin with, because I think you mentioned at some stage they're both now about equal in mass. It must have been much more massive to have evolved so much further, and presumably that is the source, together with the wind, of the accretion disk.
Yeah. Yeah, no, that's a good point. Yeah, it must have lost mass some way other than just
One question from David Boyd over here.
Sorry, Mike. Get ready with the next question.
Just keep this going, Mike.
Is the B star a BE star? Does it have a decretion disk, which is coming off the E star body? And these are rather irregular, these things. They come and go. So if that's of different size during each eclipse, that could quite easily explain the time differences you're getting.
Yeah, no, that's a very good point. I mean, BE stars, for those that don't know, these are hot B-type stars, aren't they, David, that also have an equatorial disk circulating around the equator of the star, but it's a decretion disk. It's material that has come off the surface of the star. So yeah, could this be a BE star? I don't know. I've not read that this is being suggested. So
And John Rogers again.
You can see the emission line, surely.
If I read right on your early table of the various different VV-Cepheid stars, Antares was on there. Is that true? And did I misread it? Or can you say anything about it?
Is Antares on there?
I thought so. Alpha Scorpio.
Alpha Scorpio, yes, Antares, yeah. Well, look, they are the VV Cepheid stars, so yeah, it must be a binary, absolutely. Yeah.
Anybody over there?
I was just going to say, to David's point, if it was a BE star, wouldn't you really clearly see the emission in the sort of contaminating the spectrum? You'd see the emission lines from the B star itself. Do you see evidence of that? Or?
Well, I think the pattern of hydrogen Balmer emission lines is similar, isn't it, from a BE star?
Yeah,
it can be.
That's the emission.
That's the one. Yeah. Okay.
I must thank Mike for doing all this
and it's hot, isn't
orbiting
it?
with the microphone. Yes. Right, well, we've discussed that quite a bit. Thank you very much, Hugh, again.
Pleasure, David. Honestly, thanks so much.
Our last last talk for today is traditionally regarded as perhaps the most fun part of the meeting. And here to prove that right or otherwise, we have Nick James, who really needs no introduction from me. Maybe I won't give him one at all.
Thank you, David. Right. Yes, so this is definitely the lighter end of the meeting. So just so impressive what Hugh's doing and what all the amateur spectroscopists are doing now. And there is a bit of spectroscopy in the Sky Notes, but I'll be very careful what I say because I know there are experts in the audience. Just to start off, this is a nice picture that I was very lucky to be in La Palma at the beginning of the month, and this is the Mercury-Moon Pleiades conjunction that we saw from La Palma. Has the advantage of being several thousand metres up and having a very nice clear horizon. And that will come back in a few minutes when we talk about Mercury. So, as I normally do with the Sky Notes, starting in the middle of the solar system, the Sun. The Sun is getting really quite active now, so it's a really interesting object to observe. It has been for a long time in monochromatic light, but in white light it's been really interesting to look at as well, and it's building up to quite a high level of activity, despite the fact a few years ago people were predicting that this solar cycle would be a very inactive one. It's actually looking to be quite an active one. And any of you who've looked at the Sun recently will have seen this spot group that's been crossing across the Sun. There's some really nice high-resolution images here in calcium. So it's this group, AR3014 here. There it is in slightly higher resolution. But people are getting superbly high-resolution images of these things now. So the kind of quality, and we kind of touched on this in Mike's talk about Saturn earlier, the quality of imaging that amateurs manage to achieve now on solar system objects is just extraordinary. And these are some really nice images here from Stuart Green of that region, where you can see lots of detail in the solar granulation and this just exquisite detail in the penumbral part of the sunspots. I thought that was pretty good until Lynn sent me this image. This is Philip Tosi. This is that same region, but this is just extraordinary. I mean, the detail here in the solar granules, the detail in the penumbra of the spots. This is taken with quite a large telescope. I think it's a 14-inch Celestron, but just the ability to do this. I mean, when I've tried to take images of the Sun, the main problem I usually have is the seeing is usually awful because you've got the Sun heating up the ground around you. And so to manage to get images of this quality is really quite extraordinary. But the Sun's been active not only in white light, it's been active in hydrogen alpha, monochromatic light, and there was a really nice flare, which many people observed, but this is a nice image of it that Lynn sent me. And this has been one of the brightest flares that's been around for several years, and lots of people seen that. So the Sun is definitely now an interesting object to go out and observe. You can do it in the nice warmth of the day. Don't need to get up at 2 o'clock in the morning or something to see it, so it's a convenient object to observe as well. So then on to the Moon. Lovely picture here of Albategnius, taken by Bill Leatherbarrow. This is the phases of the Moon. So the last new moon was April the 30th, end of last month. Full moon, May the 16th, and we're coming back up to new moon again at the end of this month. So the last new moon was an eclipse. So there was a small partial eclipse, but you had to be in the right place to see it. So some people travelled to Chile to see it and got a really nice sunset eclipse. So this great picture by Jörg Schoppmeier, taken from Vina del Mar in Chile, showing the partially eclipsed moon setting into the Pacific Ocean. So always a nice sight to see. I've been lucky enough to see partially eclipsed suns after total eclipses setting into mountains and seas, and it's always a fascinating sight. as these horns of the eclipse disappear below the horizon. I said it was on La Palma, and the next evening, so less than 1 day from that partial eclipse, we managed to pick up the crescent of the moon. This actually was a very important crescent because it marked the end of Ramadan. So I think people far more important than I were observing this from Morocco and Mecca. But this was my youngest crescent moon so far, so less than 1 day. And you can see there's some detail here. This was taken with the moon about 3 degrees above the local horizon, where I was on La Palma. 2 weeks after that, new moon, full moon, and of course, there was a total lunar eclipse. And the UK was, well, it was just about possible to see the total lunar eclipse from the UK. Not ideal, because it was pretty much right at sunrise, so the sky was getting very bright. So even if it had been clear, it would have been a problem. But of course it wasn't. And one of the reasons why we weren't submerged in images of the eclipse from the UK is this, pretty rubbish. There were some clear patches around, most of them sort of down in the southeast of England, some clear patches around the very east of England. So there are a few pictures taken from the UK. This one, Neil Morrison from Crawley, because the moon was low anyway, it was kind of potentially possible to get some nice images with some foreground details, but it basically sank into clouds. So here's one from on a wheeler in Crayford, Kent, just the other side of the river from me. Steve Harvey from Horsham, rather longer exposure, showing the partially eclipsed moon, the umbra, and the colours involved. I got something very similar from Chelmsford. Pretty much all of the images taken from the UK have these nice cloud features in them. And the moon basically disappeared before totality, but the sky was getting bright anyway. So Alan Tuch up in Scotland had a really novel idea. Why not use a remote telescope to observe the eclipse of the moon? That involves a bit of foresight because you need to actually reserve it at the time and get onto it. But this is a lovely picture he took remotely, from Chile. It's a composite, actually. It's different exposures for the star background and the eclipsed moon, but I think it gives a really nice impression of what a totally eclipsed moon looks like against the star background. So that was the total lunar eclipse. Unfortunately, not ideal for us, but those people who were enthusiastic and got up at 3 o'clock in the morning can at least take the pleasure that they tried, and if they were lucky, got to see something. So I showed the picture at the beginning of the conjunction of the moon and Mercury and Pleiades. Here's another one. This is from Nigel Evans, who was with me on La Palma, showing the Hyades over here, the Pleiades, and Mercury. And Mercury, of course, had a really good elongation, an evening elongation, and here's one of Martin Lewis's images of Mercury. So what planetary imagers are again able to do on planets that are hugging the horizon, always low down and very, very small, still managing to produce recognizable detail. So what you've got here is you've got essentially a simulation. This is what Mercury would look like from Messenger. You can blur it to the equivalent of what you think your telescope's resolution is and then compare it. And you can clearly see that there are features here that line up. So Mercury's gone up a lot in my estimation because as comet section director, I like planets that pretend to be comets. And Mercury does this for a very interesting reason. So Mercury's a really small planet, very close to the sun, doesn't really have much of an atmosphere, but it does have a very tenuous atmosphere, which is atoms sputtered off the surface by solar radiation. So these atoms get pushed off the surface of Mercury. They form a tail that flows away from Mercury in the anti-sun direction. And this is the detection of that tail by Mercury Messenger, the spacecraft that went past Mercury in 2008. And there's a lot of sodium in this tail, and this is where the spectroscopy comes in, so be gentle with me. So as that tail flows away, the sodium in the tail can get energized, excited by incoming light at the right wavelength, which is sodium light. So the sodium in the tail, the light from the sun comes in, makes the tail effectively visible to us. There's a big problem, though, if you look at the solar spectrum. There are these two big absorption lines in the solar spectrum, the sodium D lines, that are due to the fact that there's cool sodium in the sun's atmosphere. So all of the light that comes out of the sun that would be quite bright at these wavelengths actually gets absorbed in the atmosphere, and you have these two dark lines. So that means that there isn't much light at the wavelength that you need to excite the sodium in Mercury's tail. But we are helped by the fact that Mercury is not in a circular orbit around the sun. So Mercury has got quite an elliptical orbit, so sometimes it's moving away from the sun and sometimes it's moving towards it. And if we are lucky enough that the greatest elongation matches the time that it's moving either away from or towards the sun at its maximum velocity, those lines are effectively Doppler shifted so that there is enough light to excite the sodium in the tail. So the ideal time to see this sodium tail of Mercury is when Mercury is as far above the horizon as possible. So you want a large elongation where the ecliptic is inclined steeply to our horizon, and it's about a certain distance, about 16 days after perihelion, which is when this velocity reaches maximum. And that's just the case of what happened at the last Mercury apparition. So Chris Hooker, who does all these really clever things with filters and occulting bars and stuff, managed to get this image of the sodium tail. So here it is. Mercury's behind the occulting bar. There's the tail. Chris is using a sodium passband filter. So this is a narrowband filter to increase the contrast, because he's in Oxfordshire, where it's quite hazy and, you know, it's not at the top of a mountaintop. And so if you use a filter to isolate the sodium, you can actually increase the contrast, and here it is, definitely the sodium tail of Mercury. He got a similar picture when Mercury was close to the Pleiades. So here's the Pleiades over here, there's Mercury behind the occulting bar, and here is the tail of Mercury. So that's what you can do from Oxfordshire. Now, I was here, which is 2,100 meters up the volcano in La Palma. You can see that it has a pretty good horizon. From that altitude, the horizon's about 1.5 degrees below a normal horizon due to the dip of the height. The ecliptic was really steep. This is the crescent moon, 3-day-old crescent moon up here. So this is what I got with an unfiltered Sony Alpha 7 camera on the back of a Megrez refractor. This is not a composite. This is a single set of stacked images, color images from a Sony camera. You can see the blue emission nebulosity in the Pleiades. This field was 1.5 degrees above the true horizon at the time that I took this image. Not bad. And here's Mercury with this yellow sodium tail behind it. So you can image the sodium tail of Mercury without a filter, but you have to go up a mountain to do it. And I'm pretty sure you wouldn't be able to do this from the UK. Here's another image I took actually a few days later. Again, really nice, clear sodium tail. So I like Mercury. It looks like a comet, so it's a good planet in my book. There's been some really nice planetary formations over the last month or so, primarily in the morning sky. So Mercury was in the evening sky. All the other planets were in the morning sky. This picture by Martina McGovern, you can tell, was not taken again from the UK because the line of planets, the ecliptic here, is almost vertical. This was taken from Botswana. And at this time, it was the order Jupiter, Venus, Mars, Saturn. Jupiter and Venus swapped positions, came very close together. Here's a drawing by Paul on the day of conjunction showing Jupiter and Venus in the daytime. Here's a picture by Nigel showing Jupiter and Venus stand here, close together, Mars, Saturn. In fact, a few other things. Neptune's on there as well, and a few other asteroids. But again, a really nice run of planets. And then a little bit later, people have obviously been travelling around. This is John, sent me this from the Aeolian Islands, where you've got Venus, Jupiter, Mars, and Saturn, again, in the sky, all spread out. So all of those planets are in the morning sky. If you want to get good views of those planets at the moment, you need to get up early. Venus is gibbous phase here in these drawings by Paul. And then I've got some images here taken by Clyde Foster, who features prominently in the images I'll show in a minute of other planets, and our own Chris Dole here again from Newbury. So there are, you can see some sort of features, very, very sort of hazy features in the atmosphere of Venus there. Mars is in the morning sky, so here are some images of Mars, again by Clyde Foster, showing the planet. It'll be moving out from the sun. It comes to opposition late in the year. One of the big things this year is when it does come to opposition, it'll be at a declination of +24, so it'll be really high in the sky. So even though it won't be as big as it has been at past oppositions, it'll be much higher in the sky. So you should be able to observe Mars pretty much throughout the year as it gradually moves through the morning sky and then into the evening sky after opposition. So Jupiter as well in the morning sky is coming out, another Clyde Foster image of Jupiter. And John Rogers sent me this, which is a really interesting comparison between a strip map from amateur observations and from the Juno spacecraft, which is still orbiting around Jupiter. I think it will be for many years still. Have they announced how much longer?
2 years.
Another 2 years. Right, okay. And I think you said there's a perijove just gone. They'll be reducing some.
Days ago, and the first images have begun to appear on the website.
Right.
So we'll have another map like this very soon, hopefully.
Excellent, but really interesting again to see the comparison between amateur and spacecraft images, and again emphasising what we said earlier on, is that amateur observations of planets have got such a high time cadence. You know, amateurs can observe planets at a very high rate compared to professionals, so have a good chance of identifying outbursts and features and then alerting professionals to them. Saturn, again, in the morning sky. This is a really nice example of a transit of one of Saturn's satellites, Iapetus, which you can see just there, by Daryl Milker and Pat Nicholas from Australia. And Mike, you say there's another one coming up?
Yeah,
middle of July.
Yeah, in July on the 18th. I'm going to write an observer's charge for this because these are pretty rare events.
Yeah, unfortunately, Saturn's at a really southerly declination for us still, but you know, really potentially an interesting observation to try and make from the UK. Onto variable stars. There are lots of novae around at the moment that are still around and either fading gradually or fading slightly faster. This is one of the more interesting ones. This is V1405 Cass, which was kind of oscillating at around 7th or 8th magnitude, and it's now sort of faded down to about 10th magnitude. And Hugh showed some stuff from Annie Cannon, who'd used objective prism spectroscopy. And that technique's still being kept going by Mike Harlow, who uses an objective prism that's actually from the BAA instrument collection. And what I like about these objective prism spectra is that they actually show you in context what the spectrum of a star looks like compared to all the other stars around. So you can immediately see that a nova looks to have a very, very different spectrum to all the other stars in this field. There's very strong line emission here. Now, I know these spectra are really hard to analyse because they're unlike diffraction grating spectra, they're quite non-linear, aren't they? But they're really interesting, and Mike's doing just wonderful work, I think, looking at the spectra of these objects with a kind of old technology, but still very interesting way of observing stuff. A few other variable stars of interest, particularly if you want to do some binocular observation. Chi Cygni. Cygnus, of course, is getting high in the sky now. It'll be available through the summer. Chi Cygni is a easy naked eye object and then a binocular object as it fades. It's just about its maximum at the moment, which is about 5th magnitude, something like that. So an interesting star to keep an eye on and then follow as it fades. It's sort of very regular light curve for a variable star with this weird kind of little step in it. Does that reproduce every cycle, Jeremy, or is that? It moves around a bit. Okay. Another one that's interesting to keep an eye on is our Corona Borealis, which went through this long fade back in 2016, 2017. Whoops. Which has now recovered to about 6th magnitude with a little glitch down here. So just keeping an eye on that star to see if it should fade again. And just very recently, this star, V482 Cygni, which is another type of our CRB star, has done just that. A few days ago, it looks like it's kind of fallen off a cliff. There's a call for observations of that currently on the website from Gary Poynier. Definitely an interesting star to see what it does now. Will it keep going down? Will it come back up again? You won't know unless you go out and actually observe it. The Americans have just launched another spacecraft. This is the Starliner, which is the Boeing equivalent of the Dragon that Elon Musk does. So this is essentially a manned spacecraft launched on an Atlas V Centaur. So that's the capsule at the top. None of this is recoverable. It's a totally expendable launch vehicle. I love how the Americans do that. So it's just got launched. It says, powered by a workforce dedicated to its success. You know what powers the Atlas? Russian rocket engines. Anywho, so it was launched to put a capsule in the same orbit as the ISS, and we were lucky that that actually came over the UK very shortly after launch, before Starliner had docked with the ISS. So we could actually see it going over very close. So this is the bright thing's the ISS, the faint thing is the capsule. So if you imagine, if you could zoom in on that to see what it actually looked like, you get a picture like this. So this is an amazing picture from Chris Hooker again, showing the ISS there and the Boeing capsule here. And not to be outdone, we've got a similar one from Steve, who obviously took it with his telescope at a slightly different angle, but at about the same time. And Martin Lewis again, who excels at taking these really high-resolution images. So pretty amazing stuff that you can image, space station, but even more so that you can image a small capsule about 200 meters, I think it was, 200 or 300 meters at that time, station keeping off from the International Space Station. In terms of meteor showers, what's coming up over the next few months? Well, not a lot. The short summer nights are not really that conducive to meteor observing, but there are the June Boötids, which are active at the end of June, early July. They're associated with a comet called 7P Pons Vineca. They occur near to new moon. They have had an outburst in the past, and they are potentially favourable shower to go and observe. And then, of course, right at the end of the summer is the famous Perseid shower, which unfortunately this year is occurring almost, the maximum of the Perseids occurs almost at full moon, so it's going to be pretty much wiped out. Meteor observing is coming on in leaps and bounds, though, now, and the UK, particularly England, is absolutely covered in meteor cameras, so pretty much nothing can go unrecorded now. There's always scope for more, so if you want to set up one of these cameras, they're really straightforward, simple to set up. They're not that expensive. The basic camera modules you get from China with the lens for about £40. You join a network where all your data goes into a central server, which in almost real time works out meteor trajectories. Now, these cameras are primarily for the fainter meteors. There are other networks that record bright meteors, fireballs, potential meteorite droppers. And we've had one of those very recently, which is this one on the 11th of May. Many cameras recorded this bright fireball, including the cameras of the UK Fireball Network. So they are mainly all sky cameras. And the trajectory was worked out, and potentially this thing dropped a small meteorite, maybe only 100 grams or something like that, somewhere in the valleys of South Wales. So anyone who knows that region knows that the likelihood of actually picking up anything is pretty tiny. Unlike Winchcombe, where the fall area was much smaller, the trajectory of this fireball was almost horizontal, and so the fall zone is much bigger. And of course, in Wales, you know, this is a sort of very hilly, mountainous area. Cardiff is down here. There's lots of stuff on the ground that looks like meteorites, which isn't meteorites, that comes from all of the old coal mining and steel and everything else that went on there. So I think it's pretty unlikely that we'll find anything, but it's another good demonstration of the fact that the skies over the UK are now so well covered with camera patrols that we're able to pick up these objects and predict falls for them. So that's really interesting, and no doubt there'll be many more of those. So Winchcombe was the first example of one really successful prediction and recovery of meteorites, but there'll be many more in the next few years. And the advantage of having the video is that you know where these objects came from, so you know what orbit they had before they entered the Earth's atmosphere. So that really is helpful when you come to do the analysis of the meteorite. Anyway, all of these, well, the meteors, not fireballs so much, come from comets. And over the summer, we have one interesting comet to keep under observation. That's called C2017K2. So from the name, you can tell it was discovered back in 2017. So this comet has taken a long time to come in. It's been sort of spiraling around through the sky. It's currently about here. Over the summer, it'll be heading down through a Fucus and then to the far south where we won't see it. But it's been brightening up quite nicely. It's currently about 10th magnitude. It should probably reach about 8th magnitude, but we won't see that from here. That's from the southern hemisphere. But it's just been getting brighter and bigger as it gets closer. It's nicely placed in the sky for us to observe through the night. Here's one of Peter Carsten's images of that comet. And it's the brightest comet that we have around at the moment. There is a comet that's potentially a little bit brighter, 45P. What's the name of 45P? Can you remember? Anyway, the 45P is very low in the twilight at the moment. It's a bit brighter than this one, but from here it's almost unobservable. It's too low in the sky, in a bright sky. We did have some hope that another comet, 2021-03 Pan-STARRS, was going to be quite bright at the moment, and a nice view in the sky actually approaching the pole. But unfortunately, like many comets, it decided it was going to fall apart as it went through perihelion, and there's not a lot left of it. So, can you see that little fuzz there? So that's the cloud left by this comet, which some websites are still predicting is something like 9th magnitude or something at the moment, and it's probably much, much fainter than that. I mean, I can just about detect it with my telescope. Even if you integrate all the light from this cloud up, it's about 14th, and in reality, it's probably quite a lot fainter than that. So 2017 K2 is really the best comet to go for at the moment. But as we approach the summer and the nights get shorter and shorter, observations become more and more difficult. You have to stay up late to get any reasonable dark skies, at least from the UK. But of course, what we do have to look forward to is noctilucent clouds. So if you have a good, clear northern horizon, it's always worth having a look out around midnight to see whether you can see any noctilucent clouds. So these are very, very high clouds that form around probably dust particles in the high atmosphere. They get illuminated by the sun. So you can't usually mistake them for normal clouds because they're illuminated when all the normal clouds would be dark. They are beautiful. They have amazing structure, as you can see from this time lapse here. And usually, any pictures of noctilucent clouds tend to include the star Capella, because that star is going under the pole at the moment. So the noctilucent cloud season is just starting, so it's time to start looking out for these clouds now. The AIM spacecraft actually imaged some a couple of nights ago, and these are the first noctilucent clouds of the northern summer. So they are beginning to start now, so from now on through till late July, it's worth just keeping an eye out every clear night to the north to see if you can see them. Sandra Branting of the Aurora and NLC section will send out alerts if you register with her website, so you'll know to go and look. Paul, who I see has scarpered, sent me a video from last night. Now, they've just installed an all-sky camera, and they picked up these bright clouds on the northern horizon this morning. Now, I think, because they're moving with the lower clouds, that these are actually just cirrus clouds being illuminated by the sun in the dawn. Generally, with noctilucent clouds, they move much more slowly, and you see the lower level clouds moving past the noctilucent clouds. But I'm sure this all-sky camera will pick up examples of NLC through the summer. I have, at this time of year, a camera that I just set up to take images, colour pictures looking north throughout the night, so that if there are any NLCs, I'll have some images of them the next day. So that's really a thing to look forward to through the summer. The planets in the morning sky require you to get up early, but all the planets are there for you to see in the morning sky. Variables to observe. Hopefully we'll get some nice weather through the summer so that we can do all of this. The next time we're here is October, is it? So by then we'll have got through all the summer. We'll be back heading towards the winter, and we can kind of look forward to that. But so that's the Sky Notes. I'm always happy to see that we've got such an active set of people observing for the BAA. The members' pages on the website are a great resource for me doing Sky Notes, because I can just go there and see what everybody's doing. And I'm just really impressed what our observers and imagers are managing to do now. So thank you very much.
Thank you very much, Nick. So we've run out of time. That's all from us for this month. Hope to see some of you at the Nottingham meeting, 28th of June. 25th. Thank you very much. 25th of June.
You'll see fewer people on the 28th.
Yes. We're back here for the AGM in October. Yep. So that's the close of this meeting. Thank you all very much, and thank you for the 20-ish people who attended on Zoom as well. It seemed to increase at the end. I think you attracted, your mass attracted.
Oh, I'm sorry. Excellent.
Your intellect attracted them.
What, like a black hole attracts things?
You might say that.
Yeah.
Yes. Right.
Okay.